Go. Now it's going. All right. So hello everyone. Let's see. I'm going to cover a few different small topics that really wrap up on chapter 4 today. And if you go back to my first lecture, when I told you why I was doing this filming of the lectures, of course it's for the students to go back and watch them again. It's for me to monitor my performance, and it's for me to fix mistakes. And last time I was clearly not in my best shape because I got stuck with an eraser in my hands. I was just trying to figure out complicated sequences of angles to show you why you have a singularity with a 3-2-1 sequence. So I took the video from last lecture and edited heavily because it wasn't that great. So it took me like 4 hours to come up with a video that makes sense. So please go back and watch it. There were a couple of imperfections there that I tried to fix, and I'll go over them again very quickly. So the first one was, okay, if this is my object, and x is pointing at you, y is that way, z is up, and I do a 3-2-1 sequence of other angles, I claim that if the second rotation is 90 degrees, it doesn't matter where the first and last are, you end up in the same physical configuration if their difference is the same. And so if you do a test, well, you go back at that video. If you do 90, 90, 90, for example, you do 90 degree on the z-axis, 90 at the y, which is now pointing at me, and another 90 on the new z-axis, which is pointing down, which means you do this. This is how you end up, right? So this writing is looking at you. But it's the same as doing 0, 90 on the y-axis, and another 0. I end up in the same physical configuration in space. And I've been able to represent this configuration of this object with respect to the room with 3 different combinations of all the angles, which is not what you want. Again, you want a unique relationship between 3 numbers and a physical configuration for the object in space. And you can do the same with, I don't know, 45, 90. Let's do a minus 45. So it will lead me to this one. It's you get here by doing 90 and another 90. So as long as the difference between first and last angle, it's the same in this case, you get infinite combinations of the first rotation and the last rotation that give you the same physical orientation, and that is not a good idea. It means that you're just choosing parameters, in this case the 3-2-1 sequence, that fail at that particular point where the second rotation is 0, right? So that was, I was just in my head thinking about way too complicated combinations that I needed to do. And then we did this. We said at some point, okay, the angular velocity of the object B with respect to A, we said we want usually to express this vector as projected in the basis which has the 3 primes. Is it working? Is the audio moving? Yeah, that's a big concern. Otherwise, I would have to do everything again. And so what that means, in other words, is that we wanted last time to find this kind of expression, right? Omega BA on the first axis, x triple prime, plus omega BA on the second axis, y triple prime, plus omega BA on the third axis, z triple prime. So this is basically what I was looking for. And these are just scalars that represent the projection of the vector, omega, on that particular basis. And we have found that if I choose, for example, the 3-2-1 sequence that pertains to orbital parameters, in particular, you get some matrix here, which is a bunch of sines and cosines of those 3 angles, that multiplies the column vector of big omega dot, I dot, and little omega dot, right? And if you want to be thorough here, by multiplying a 3-by-3 matrix times a column vector, you get a, what do you get? You get a column vector. So to be completely accurate, I can imagine that I multiply this times a row vector, and so you get that kind of expression up there, where this first row times the column gives you omega 1, second row column omega 2, third row column omega 3. That's what we had done last time, right? We found out what this matrix is in MATLAB, which again you can do by hands. It's not that huge of a deal. And let's say that we call this matrix A, just for fun. At some point I said, well, I'm not completely happy by just stopping there. I'm going to invert the matrix and basically look at this expression the following way. Basically, I'm going to write that big omega dot I dot and little omega dot are equal to what? To A inverse that multiplies that vector of omega, which is again omega b with respect to A first component, omega b with respect to A second component, omega b with respect to A third component, right? That's what we had done, again, in symbolic MATLAB, but that's basically the operation. And I said, look at this matrix here, A inverse. It does not invert if I, the second rotation, hits 0 or pi, because there is a sign of I that divides everything, right? It's the determinant of A. Why do I care about even getting to this expression? Why did I want to invert that? Because the things that you can actually measure, and again, I tweaked the video to correct that, it's this vector. That's what you would measure on board. Again, if this is the basis attached to your moving vehicle, again, think about an aircraft, a spacecraft, right? Your gyroscope, whatever sensor you have on board, will be able to measure a vector in its own basis. So these three quantities are things you measure. So these are the measurable quantities that you will have from a gyroscope. Measurements, okay? So you will have that. That will be a given during the motion. And so if you are given the angular velocity at all times and initial conditions, omega 0, I 0, and little omega 0, then you can integrate these three differential equations, right? The same that we have done with ODE 45 for the orbits. You have differential equations, you can integrate them numerically, for example. Do we agree that these are three differential equations? Non-linear, because there's a bunch of sines and cosines in here. And this, again, you can treat this as an input. But you basically get three equations for omega, I, and little omega. They're all coupled, of course, but that's what you get. So if you know the orientation at a certain time of your vehicle or your orbit, since we've used these angles to represent an orbit in space, and then for some reason that changes, it will change because there is a rate of change of the orientation given by this omega, and this is how you can follow basically the trajectory of that orientation. Always do the parallel in your mind. What do you do when you track a point in space? If you are given the velocity of a point in space, you can integrate these equations of motion, which are pretty simple, right? If someone gives you the evolution in time of the velocity of a particle, this is what you integrate in time. Given an initial position and how v changes, you integrate those and you get the trajectory. X, y, and z as a function of time. Numerical probably, but you can plot that. You can get it. The same happens here. It's just that it's not, these equations to integrate are not as nice as these ones because there are sines and cosines, but the principle is the same. You are given an initial position for your object in space. If you can measure how the angular velocity is changing with time, you can start from that initial condition, integrate these equations, and you will have the trajectory, meaning omega in time, I in time, little omega in time, for the orientation of the object. Make sense? And I have posted exactly that in MATLAB. So you have the symbolic calculation for this matrix A and its inverse, and then I have a main function and a differential equation function that I integrate with ODE 45 for the 3, 1, 3 sequence with some initial conditions that I picked randomly. So you can play with that. Try, for example, to tweak that with initial conditions that have these at 0. If you stick a 0 there, exactly 0, you will get a bunch of nans from MATLAB, right? Because that will actually be a sign of 0. So MATLAB will recognize that there is a problem and it will, spit out a bunch of these. Okay? But if you don't start from this exactly, and you run a simulation which happens to go across 0 for this angle, or pi, MATLAB is not going to fail on you. It will continue integrating because it never really finds a sign of 0, right? Numerically speaking, it's going to be very unlikely that you hit sign of 0 exactly. So it will keep going. But you need to know that at 0 or pi, there is a singularity, so you should really not go through that in practice. Yes?
What if the first
they're fine. Singularity for Euler angles only occur because of the second rotation being 0 pi for a symmetric sequence like the 313 that we have seen, or for an asymmetric sequence like this. It's again on the second angle, in that case being 90 or, well, I guess 270 is the same. Right? So that's all. Those are the limitations of Euler angles. Why do we use them despite these limitations? Because they are angles. Even though you may think that it's complicated to visualize them, you can still visualize them. We have gone through single axis rotations, you know, one and then a second one and then a third one. You can see them. So they are very visual ways, parameters to represent orientation of an object. There are other ways, which we're not going to see probably in this class. You would see them in an advanced astro class or spacecraft attitude dynamics class, such as quaternions, where instead of using 3 parameters for the orientation of your object, you use 4. So you have redundant sets, but having that 4th redundant variable eliminates any singularity. The downside is that quaternions have no visualization in space. They are just mathematical quantities that you cannot visualize, like I do with angles. So we do use Euler angles quite a bit because they're visual, and because if you are aware of the singularity, you can always switch and, and bypass it. And in some cases, you may know that your motion will never hit a singularity for a particular sequence. Again, if this is an aircraft using a 3-to-1 and the second axis is the roll axis, you probably are not going to see 90 degrees, because if you see that, you have other kinds of problems, right? So that is why they are used. I posted another uncollected homework which basically asks you to do everything you already have in MATLAB, symbolic calculation of this matrix and its inversion, and then integrating the 3 angles in times for the sequence 3-to-1. So you basically have everything laid out there. You just have to go by hands. I recommend you do it by hands, figuring out what kind of rotations, matrices you have to involve. Since in this case we had, what did we see? We ended up having just 2 types of matrices, right? What I called a type R3 and a type R1. So for the sequence 3-1-3, you end up writing an R3 of big omega, an R1 of the inclination angle, and an R3 again of little omega. And then you need to know how to combine them. Well, for a 3-to-1, you're just going to see an R3 of, let me just start calling them alphas. Alpha 1, and R1 of alpha 2, for example, well, let's just call this R2, just to be consistent, and this is alpha 3, and R1 or alpha 1. So basically you're going to see a new type of rotation matrix, R2. But the idea is the same. Single axis rotations. You have a question about this? Is it clear what you need to do? So 3-to-1, you go about this axis, create the new intermediate axis. Instead of going on the x, you go on the y. The second rotation is here, which is going to move this axis here and the x down, and then you do your last one here. And the axis will move somewhere else. But the single procedure, each step by step, is the same. So try to do that by yourself, because it's a good exercise. One more thing about Euler angles, before we move on to more interesting stuff, in my opinion, is why do I need 3? We agree that if we're tracking a point in space, it's, he has 3 degrees of freedom, x, y, z would be enough. Why do I need 3 to represent the orientation of a reference frame / rigid body? For us, they are the same thing. So if I call this rigid body or reference frame, as far as we are concerned, it's the same. Why do I need 3 parameters for the orientation? Remember this? What is this? 3 non-collinear points whose mutual distances don't change with time, right? And this may be a rigid body. It's a triangle with 3 masses and very light, connections here. They may even have a mass. I don't care. As far as I'm concerned, if these 3 masses remain at a constant mutual distance, it's a rigid body. And if I am interested in rotation only, I can imagine that one of the points is really not going anywhere, and the other 2 are moving, right, around that point. So if I have 3 points is what? 9. I would need in principle, if I'm tracking 3 points in space, I would need 9 coordinates, right? X, Y, Z for each of them. But there is a constraint that these two have the same distance, these two have the same distance, these two have the same distance, and this is not going anywhere. So that removes 6 of them. 1, 2, 3, and I just sit myself on one of the points because I care about rotation only. So really, to tell me basically where these other two are with respect to this guy, I only need 3 variables. Make sense? It's the idea of degrees of freedom, which again, it's explored in dynamics in more details. Here we just use it. But the degrees of freedom of a particle in space, in 3-dimensional Euclidean space, are 3. If you start removing with some constraints, those degrees of freedom, you need less. So again, I would need, fix yourself in 1. 1 doesn't go anywhere. 2 and 3 can rotate about 1, but they need to remain at mutual distances that are fixed. So I would need 3 coordinates here, 3 here, it's 6, but then I remove 1, 2, and 3 of those degrees of freedom because I need to maintain fixed distances. So that's why you represent rotations with 3 parameters. That's why 3 angles are enough. Okay? All right. So try to do that exercise by yourself. Now we're going to move to basically MATLAB mostly. But it's a couple of things that have to do with orbital parameters, especially one. So I have introduced this A, E, I, what is the sequence? Big omega, little omega, and through anomaly. And we said, these are an alternative to x, y, z, x dot, y dot, z dot to locate the orientation and the shape of the orbit in space. And then once I have the orientation and the shape of the orbit in space that is given by these first 5, this is an equivalent of time. It just tells me where I am on that orbit that I have located clearly in 3-dimensional space. Why do we even care about this? At this point, it's probably not that immediate to understand, but I'll give you one example. And one example are Sun-synchronous orbits. We are not studying perturbations. So up to this point, we haven't done anything. I gave you a function that integrates the equations of gravitation if you have what we call J2, which is basically the planet being not a sphere anymore, it's an ellipsoid. I squeeze at the poles and I take into account the bulging at the equator, and I just gave you that function, and for now we just believe it. We'll prove it, but let's practically see what happens. You can play with a combination of appropriate combinations, there is not only one solution, of semi-major axis and inclination to obtain these two. These sun-synchronous orbits. And I'll need to define what they are. So let's see. What happens is that we have the ECI, fixed coordinate system, which we have defined in such a way where the x-axis points at the Pisces constellation. Z is the north, south-north axis, so N, and then the Y completes a right-handed frame, and I have my planet here, right? And if, let's just imagine that this is, I don't know, it's the fall. So if it's in the fall, the sun happens to be exactly on the x-axis, right? The sun is exactly on the x-axis, only on the equinox line, which means first day of fall and first day of spring. So spring will be here. But anyways, let's say that this is fall. So what is really happening is that my planet is going around the sun on its trajectory, whatever that is. So it will move, right? It will go around. And let's say that I would like to put a satellite into orbit so that the satellite can always see the sun. Solar panels, that's what we use on satellites, right? And let's say that I'm able to do that, and let's say that this is just an example. This is my, I want to use a different color, which is probably here. For the orbit, let's say that this is my orbit. Oh, why do I pick the green? I don't know. I just like green. Okay. This is my orbit, goes up, comes down on the other side. So this is the north part of the orbit. and then the south part is the dotted line here, so it's below the equatorial plane, and say that it's built, I inject my satellite into orbit such that it's always facing the sun, right? That's possible. As long as the plane that contains the orbit, extreme case, is exactly at 90 degrees with the line that connects the sun and the planet, I can get that, right? But it's not the only solution. If the orbit is big enough, and even if I'm not exactly at 90 degrees with the sun, I see the sun. And let's say that I'm able to do that, and my corresponding, so this will be the line of nodes, of course, and this is my right ascension of the ascending node at that particular day when I launch the satellite. Then my Earth goes around, and I end up here. And remember, ECI's directions remain the same. They don't change, right? We don't want that to change. So my x, y, and z axes remain the same. If I had the same omega, ran, I may be in trouble with that idea of seeing the sun all the time, right? You see that? Nothing is to scale here. I'm not, telling you the same major axis of this orbit. But the idea is that at some point you may have the planet in the way. The Earth may be covering your satellite, right? You don't get sunlight. If omega remains the same. What if instead I can play with that omega? So omega now is not a constant anymore, and I can have it in such a way that now the line of nodes is up here, as past the y-axis. So if I were able to do that, I may still find myself in a situation where the orbit is actually facing the sun. You see that? So if I were able to rotate that line of nodes at the same rate as the rate of the Earth going around the sun, so assume that at initial time you are looking at the sun for the entire orbit, and that's the plane of your orbit. And the Earth goes around the sun. If you can rotate the plane of the orbit, in other words, you can rotate, change big omega along the entire year at the same angular velocity as the angular velocity of the Earth around the sun, then you are sun-synchronous, right? You're chasing the sun, right? Well, any questions on this kind of 3D explanation? Yes?
You said you changed the node, you changed the omega.
Yes. You would change the omega. So say that I'm able somehow to bring the new omega to this value, so that my plane of the orbit is still able to show me the sun at all times, so that the Earth is not in the way. Then I would get a sun-synchronous orbit. Now, as in everything we get from nature, there is a plus and a minus. J2, the perturbation because of the planet not being spherical, is most of the time annoying, but in this case, it does help us to get that. And I'm not going to write the actual equation, because we'll have to demonstrate it when we get to perturbations. We'll just prove it with MATLAB, visualize it. But there is an equation that tells me how omega changes in time, which is a function, as I told you, of semi-major axis and inclination. So there is a way for you to choose the right semi-major axis and inclination so that that omega dot is what you want. And in my case, what I want is that this has to match the omega, the norm of the angular velocity of Earth with respect to the sun. These are all scalars, okay? And we have proven what that number was some 10 to the minus, I have it here, 72 10 to the minus 6 radians per second squared. Radians per second, I'm sorry. So we do have that. I'm sorry, that's the angular velocity of the Earth around this axis. It's about 2 pi over 365 days, right? Plus that additional rotation that we have discussed when we talked about geostationary orbits. So there is a way to match this rate to be what we want. In this case is how fast the Earth is going around the sun, so that that plane is following the sun by just using nature, because of the planet not being a perfect sphere. And let me show you what happens when you pick that, just in MATLAB, just to prove it to you. Again, I'm not going to give you explicitly this formula. It's in your chapter 4 if you want. but I think it's misplaced in the book because you really first want to talk about perturbations and then prove those expressions. But they just use it there, I believe, to show why we even talk about orbital parameters. So this should be a pretty clear example of why we talk about orbital parameters. Because imagine trying to build a Sun-synchronous orbit talking about x, y, z, x dot, y dot, z dot. It doesn't seem so intuitive to me, while if I can play with the variable, in this case the ran, that has to do with the plane of the orbit. I don't really care what my satellite is on that orbit. As long as the plane looks at the sun, I'm fine. That's all I want, right?
Is the satellite also rotating around the Earth?
Of course. Yeah. The satellite is going around the planet, of course. Satellite is you know, it's here, it's here, it's here, it's here. But all I care is that the plane containing that motion is never covered by the Earth. So the satellite doesn't want to see the Earth when it's trying to look at the sun, doesn't want to have anything in its way. These are very useful orbits, so you get continuous power provided to your solar panels. So this is a MATLAB file. Can you focus on that? Usually we can, but I probably have to shut off the lights. It does eventually focus on MATLAB. Yeah? Okay. So this is a MATLAB file that, well, the core of this is really, it's kind of a long one I put together. It does several things that we're going to discuss today. But the core of this is nothing new. It takes the case when you don't have the mu over r cubed r only, but you also have J2. So remember, that function is there for you. And we'll demonstrate how we get to that kind of force model. Basically, it's a more elaborate force model that takes into account oblateness. And so what I'm doing here, the first thing I'm going to run is, it's exactly a Sun-synchronous orbit. So I choose orbital parameters that give me a Sun-synchronous orbit. By looking at this expression, I can match the rate of change of the ran to be the rate of change of the Earth around the sun by choosing this semi-major axis, and to that altitude I have this corresponding inclination, which is more than 90 degrees. So this is, going back to one of the questions I had a few days ago, there are cases where you do go above 90 degrees inclinations, but there are very rare cases like in this one. And so if I run this, which is probably going for 10 days, so it may take a while to run, it will pop up a bunch of plots, but I really care about one for this specific example, maybe two, where I'll show that if this is time, and here I have omega dot and, omega and the, basically the, what do we call this? The angle of the, let's call this alpha. Alpha Earth with respect to the sun. So where is the Earth with respect to the sun? Other than some initial condition, they basically go at the same incline, same rate. That's what I want to prove. If I can get a plot like that, then given that at initial time I am looking at the sun, then I'm going to follow the sun, right? Make sense? So forget about this one. I don't need it now. Forget about this one. We're going to talk about ground tracks in a few minutes. That's what I get. So if I choose the right combination, like in this case, of semi-major axis and inclination, they should look the same. So that's the plot of, well, I call it Earth's angular velocity. It's really not true. It will be the angle of the Earth around the sun. I'll fix that. So it does increase at the same rate as the ran. The ran wasn't starting from 0. So, but the ran, again, the initial ran, it's up to you to choose. So if you want to build the Sun-synchronous orbit at the first day of fall, you need to figure out what is the required initial ran, so that you are in the sun then, and then you follow it. If it's some other time during the year, it will be a different initial ran. So, yes?
Do you make the adjustment by like increasing the speed of the satellite itself?
No, you basically just, again, that expression only depends on semi-major axis and inclination. So you just have to make sure that your orbit has that semi-major axis. When you launch the satellite up, you need to make sure that has that same major axis and that particular inclination. And I think in this case it's actually circular. So I think I have a zero eccentricity. So you can basically get an orbit that has that altitude, 758 kilometers, because that's the radius of the Earth. So this will be the altitude of my orbit. make sure it's at this inclination, which is the difficult part to get. That's a pretty high inclination. And if you launch from the equator to get there, it's going to be very difficult, as you can imagine. We all launch usually as the rotation of the planet in the same direction. And then if you need to change orbital plane, you need to do corrections. We haven't talked about maneuvers yet. But changing the inclination is very expensive. So these orbits are actually expensive fuel-wise to obtain. But once you are in at that particular inclination, at that A, and you need to be at the right REN, so there's probably going to be a bunch of maneuvers to create your initial orbit facing at the sun with the right altitude and the right inclination. Once you get there, you let it go. It follows the natural behavior due to the oblateness of the planet that is causing this to not stay constant. So remember, the force model we have defined up to this point, telling me that r double dot is minus mu over r cubed r. This is a simplistic model of the attraction of the planet on our spacecraft. This is not reality. There is more than this, which is what you have in your J2 acceleration function. In that case, these don't change. They remain fixed in time. The first 5 orbital parameters do not change if you have a perfectly spherical planet with uniform mass distribution. It's the same as saying that the angular momentum of the orbit does not change and the eccentricity does not change. What we have proven at the very beginning, right? So remember that those map into this. Right. You will not be able, by only using nature, if the planet was a perfect sphere, no oblateness at the poles, it will not do that. It will not change plane. So basically this is the initial plane, and it will go around like that, and it's not going to change. But nature is there, and it's helping us. So here you use nature at your advantage. In some other missions, the fact that you have J2 may be detrimental. You may not want the orbital parameter big omega to change. So, but in this case, it's a plus. And so that is one of the most obvious examples of looking at orbital parameters. Because again, since they give me the orientation of the plane in space, the shape of the orbit, I can play directly with those, like in this case. In this case, I only care about the plane. As long as the plane is looking in the right direction, I get sun. And that's all I want. And it's easier to do it with orbital parameters. So that's the first example I wanted to bring to your attention. And then let's talk about something else. Any other questions on this? Again, you're not expected at this point to know why the formula of the acceleration with J2 that takes into account the oblateness of the planet is the way it looks. I just gave it to you. We'll go through perturbations, but I thought it was important to show you why we talk about orbital parameters, and this is one of the examples why. Because they actually don't stay constant in reality. You can play with them. Okay, what is another important thing to know when we talk about satellites? Do we have an idea what ground tracks are? More or less. I'm sure you've heard about them several times, but what really they are is you again go into your ECI basis, X, Y, and Z, and you have your planet here, whose center is the center of this coordinate system, right? And your satellite is somewhere here at a given time, right? Spacecraft, okay? And there is always, if you imagine that the planet is a sphere as a first approximation, there is always a point intersection of that sphere and that vector, right? You can imagine that. And as the satellite goes around its trajectory around the planet, and by the way, the planet is rotating about the z-axis as well with a certain angular velocity of the Earth with respect to the inertial frame, this trace that this intersection point will leave on the planet can be, whatever it is. The planet underneath is rotating. The satellite, depending on its orbit, is doing its motion. So as time goes by, the sphere rotates, the planet rotates, the satellite goes around. the ground track is exactly what you can imagine, is the track of that is tracing that point, intersection of position vector and the sphere that represents our planet. So it's very useful to be able to reproduce the ground tracks of satellites, and what we do usually is using something a little more friendly than looking at 3D images. We use what are called Mercator maps. And this is the last name of the gentleman who introduced these kind of maps. It's nothing special, really. You basically report on, so here you will see all the continents. I don't want to even try to draw anything here. But it's a rectangle where you see the map of the, put on a plane of the planet. And here you have minus 90 degrees latitude. This is your 0 latitude, equator. 90 degrees, so this is minus 90 or 90 south. This is plus 90 or 90 north. On the x-axis, you will have 0 degrees. So this axis will be Greenwich, the meridian of Greenwich, London if you want, UK, 5 hours ahead of us. And here you have 360, which is going around in longitude. So this is your latitude here, and this is your east longitude. There are different versions of these. Sometimes you see just 90 here and 90 here. You need to remember that this is south and this is north. Sometimes you see the 0 in the middle and you have 180 west and 180 east, or 0 to 360, like in this case. It doesn't matter. You go around once and once you hit 360, you are at 0 again. So in this particular b-dimensional representation, we do try to trace this point. So again, altitude here is outside the picture, of course. I don't know how high the satellite is, but I know which point is looking down exactly on the planet, longitude and latitude. So height is out of the picture, but it's still pretty useful, right? And so here you start plotting whatever comes out of that, and then you go around once, and this will reappear maybe, well, he has to reappear at the same latitude up here, and it repeats itself, and it goes on, depending on how many days or hours you do that, right? And depending on the motion of the satellite, on which orbit it is sitting. Now, there is a problem in computing this. Should probably do another sketch here. It would be extremely easy to find, those are two angles, right? Latitude and longitude. If I remove the Earth from the picture and I look at the position vector only, r, well, it's pretty easy to find these two angles, right? Project r on the xy plane and call this your longitude, and which we also called right ascension of the position of that object, and call this latitude, right? That would be pretty easy in ECI. I can do that. I just have r, which is xi plus y j plus z k, with some arc cosines and arc sines. I can figure out those angles, right? What is the problem if I want to tell exactly now where the satellite is seen, longitude and latitude on the planet? What do I need? What piece of information am I missing here? Earth is not sitting still under this thing. It's rotating. So I need to know basically where the 0 is at all times. I need to know where the planet is. For that, so in other words, if the meridian of Greenwich is at this particular longitude at that time, I need to subtract this. I need to subtract this alpha Greenwich, right? Correct? So there are functions to do that, which I actually posted. You have them. These are the two. They are just given to you. You can just use them if you want. They're not that complicated. So this GST time function takes Julian date, basically the date now, day, month, year, the time, etc. We'll discuss that in a second, and returns this angle. It tells you where Greenwich is. at a particular date and time. You don't input just a regular date and time. Julian date is actually a number that tells you how many days have gone by since a certain day which occurred 4,700, I don't know how many years before Christ, believe me or not. That's what they do. So before I'm able to input a Julian date in this function, I have to compute the Julian date. And there is another function to do that, which again is given to you. You can just use it. You can look inside of it. It's really not a big deal. In this function, you use actually year, month, date, hour, minutes, seconds. So this converts the actual calendar date that you will use into a number. And I think that date, which was a few days ago, 20th of February, ends up being like 2,500,000, I don't know how many days. It's a huge number, but that's what it's used. That's what people use. And you input that in here, and GST is this angle here. And so, in other words, if you have your satellite, let me just play with another example here now. In a certain orbit, you can compute those angles that I gave you, ignoring the planet, and then subtract the motion of the planet, right? Underneath. Now, so I have to fix the longitude for sure, because the planet is rotating. Do I have to fix the latitude? What do you think? You think I have to fix it? No? Yes? Maybe? I don't, right? Latitude doesn't change. If the planet is rotating underneath, the latitude doesn't change. That angle is there. I don't need any correction. The XY plane is the equatorial plane of the planet. So if I see the satellite being at 30 degrees north latitude, if the planet is rotating, if the satellite is 30 degrees north latitude, if the planet is rotating or not, it's not going to change this angle here. Yes?
So what you're saying is longitude has to be adjusted?
The longitude has to be adjusted. So in other words, ignore the fact that the planet is rotating first, compute these two angles, and you should be, comfortable doing that, for sure. For example, if I look at, so this is the z, right, of r, and this is the y is here, and the x is here. How would you compute the latitude angle? What is the relationship? Z is what? Z is r, the norm of that vector, sine, right, of the latitude angle, right? So if I give you r, x, y, and z, well, invert the sign here and you find the latitude, some kind of approach for longitude. So just find those two angles, ignoring the planet. Then the latitude is set. You don't need to fix this. You need to fix the longitude because the planet is rotating under, right? So for example, I have this simulation here that runs, let me reduce the time because we are running out of time here, just for a day. I have the data now. By the way, this program I have takes orbital parameters, then converts, as you should have done in one-year homeworks, into r and v, Cartesian coordinates, and then integrates the equations of motion. So this data I have is for a geostationary orbit now. So that height right there, here, this is the height of the geostationary orbit, which we have discussed in the past. Circular, of course, zero inclination, otherwise there's no such a thing as a geostationary orbit. The other ones don't really matter. So what do you imagine the ground track of a geostationary satellite to be? What are you looking at from a geostationary satellite? Those are the satellites that give you your TV. You have your dishes that look at a certain angle from here, 29 something angles in a certain direction. So if this is latitude and this is east longitude, okay, and this is 0, and I select a 0 inclination, so your satellite is in the equatorial plane, I want a ground track that it's just a point. That's what I want with the geostationary satellite. It needs to look down at the same point, right? And so let's see if this is what it's doing. Well, forget about this Gainesville point. We'll discuss that in a second. That's the location of Gainesville. This is, in a day, what my satellite is doing. Nothing. Sitting there at 0 latitude And, well, yeah, the longitude is changing a little bit, but quite frankly, it's changing on the second digit, third digit. So it's there. It's just sitting there. It's looking down at the same longitude on the planet, which in this case, I don't know what I picked, 23 degrees, 0.8, something like that. That's what I want, right? Now, this is if you have the luxury of being able to go into a equatorial orbit at 0 inclination. The Russians didn't have that, so they have what they called Molniya orbits, pretty eccentric orbits, as you can see, 0.72. Let's see, Molniya, this is the right inclination. So what they create is they create a ground track that allows you to spend as much time as possible in a certain, forget about this one, at a certain longitude. Again, with your geostationary satellite, you decide you want to look down at the center of, North America, and you stay there at that particular longitude. In this case, say that you want to spy as much as possible this longitude here, I don't know what it is, 70 degrees, whatever that is. I just enter some random numbers for the other orbital parameters. So this is your ground track. As you can see here, you're spending a lot of time. You go up there and then you come down. You spend quite a bit of time looking at the same, more or less the same location down on the planet, longitude-wise. That is the apogee of the orbit. That's why it's a very eccentric one, because up here you slow down, right? Apogee is the smallest velocity, so here you go by quickly. Up here you slow down, and your velocity, the orbital parameters have been chosen so that your velocity tries to match the velocity of the planet for as long as possible. Of course, it's not ideal, it's not a geostationary orbit, but it does spend quite a bit of time on the geographical location that you want. And this is also something we'll be able to prove when we are able to find differential equations for the orbital parameters. You can play with the orbital parameters to make your orbit do what you want. And then another example, because we're running out of time, that I really wanted to run was, okay, let's comment this out. So a few days ago, I was looking at the sightings for the International Space Station in Gainesville. So I looked it up, and this is the link I gave you where you can get the orbital parameters for the station at certain days. So this is day 51 of this year. January is 31 days, so this was the 20th of February at this particular time. So I was able to download the orbital parameters at this particular time. And then I looked at another website where they give you when the ISS was visible from Gainesville, and it was the same day as 7:35 p.m. local time. So 7:35 p.m. here. The times you have, you need to be careful what time you're using. The times that they give you for the orbital parameters from the station, this is Greenwich time. So what this means is that it was 7:35 for us. It was midnight and 35 minutes of February 21st for the UK. And so I said, okay, I'm going to integrate the equations of motion for about a day with these initial orbital parameters, subtract the rotation of the planet. Everything is done here because I am computing at this particular time, the 20th of January at 12:25, the Julian date, converting to the GST, etc., etc. I compute here exactly what I told you before, latitude and longitude, without even caring about the planet rotating. So I just do an arc sine and arc tangent. And then I correct the longitude with this operation. I subtract to the longitude I have here the position of Greenwich meridian at that time, plus how much time goes by after that. This is the angular velocity of the planet. The modulus operation just allows me to have a result that is between 0 and 2 pi. I don't want to go above 2 pi because it doesn't make any sense. Okay, so this was the ground track for a day. I think I was doing a day, right? Up here I have that little star there, it's Gainesville. We are about 29 plus degrees north and a certain east longitude. We are, of course, east. Sorry, we're west of Greenwich, but since I'm going 0 to 360, I have the east longitude. I'm just going around from Greenwich. And that is the small red star, is the closest I get to the station, according to my ground track software. And it looks like it's making sense, because this is the time that goes by, 12.2 hours after the initial condition that I gave you. And what was the initial condition? Was, again, noon. Where is it? Right here. It was this one. It was on that day, the 20th of February at 12:25. So if you add 12:25 plus another 12 hours, it's about midnight and 25 plus a few minutes. So it looks like it's matching what the other website was telling me, that you were able to see the station at 7:35 p.m. Gainesville time. So this is what you do with ground tracks, for example. They're very powerful. You want to know the projection of the satellite on the planet so that you can see it, so that the satellite can see a certain location and can take pictures, whatever is your mission. Ground tracks are a must. For a given satellite, you need to be able to track it on the ground. And also, you may want, as in the case of geostationary orbits or Molniya orbits, you know what kind of ground track you want to obtain. So we'll get there. We'll study the differential equations that give you how the orbital parameters change, so that you can build orbits of a desired behavior. Again, Sun-synchronous or Molniya orbits or something else. So this software here, I really think you should start by yourself. It looks long, but I'm doing a bunch of things that are not that difficult. I encourage you to start playing with the idea of computing these two angles without the Earth rotating under it. Okay? And then we can talk more. You can come see me at office hours about how you correct for the rotation of the planet. But again, it's just these two guys here. Computing the Julian date and where the meridian of Greenwich is. Isn't this cool? This is cool. I was pretty excited I could track the station, you know. Took me a while, but it is possible. Questions, concerns? Okay, enjoy the break. I think we all need it.